Hi guys, this is Paul again. I've got another new video to show you, and I'm calling this Quad Step 288 3D Helical Order. In the last couple of years, I've shown a lot of work with phyllotaxis, quad step phyllotaxis. For example, I showed that you could produce the geometry, the 3D geometry of a pine cone using quad step. I also showed that the geometry of a pineapple or the 200 seed pattern of a strawberry could be produced by this method. Now this is something very simple, but there's something to this 5-point division of 4 angles. Now look at this section of B-type DNA. I show little red balls in the sequence of rotation of the rungs. Let's hide the red balls and bring in the colored balls. Now look at this. It starts with the red ball, then it goes to the yellow ball, then it goes to the purple ball, then it goes to the cyan ball, and he returns again with the red ball. Now this 4-angle sequence between 5 colored balls can be used for the 3 types of DNA. I show it in my last video. I can show you the name. Now think about it. The rung information of 1, 2, 3 and 4 can be swiveled on 5. Now I showed this swivel to a different vector in my earlier videos. It has to be an obtuse angle I show. I also showed that going from one vector to the other vector involved a helical turn of 180 degrees. This seemed to give a real smooth flow in the helical curve. Some people show DNA going around a triangle in acute angles. I don't agree with this because it does not take a smooth flow, and it also looks very shitty. Okay, now we'll make a start on quad step. Now in front I show 3 colored spheres. I can actually call them balls as well. Now I've turned down the opacity on these 3 balls so that you can see 3 white rings. Now these 3 white rings are linked together in a hierarchy. 3 to 2 and 2 to 1. Starts with 1. Okay, look what happens when I give each ring an 120 degrees turn over 150 frames. Now we get the hierarchy angle by dividing the number of balls into 360. So this is 120 for 3. Okay, now we can repeat the process for a 4 ball. And this is going to be at 90 degrees. Now the next one is going to be at 72 degrees, and that should give us 5 balls. And next we're looking at 60 degrees, which will give us the hexagon. Okay, the next one is going to be 7, and this is a real funny angle. Let's take a look. Now this angle comes to 51.428. The number 7 seems to be on its own. Okay, now we've got the number 8, and that will be 45 degrees. This is the first time that the quad step colors are working out correct. Some people might think I'm daft, but I really think the quad step is onto something. Okay, the next one is going to be the 9 ball, and this is going to be 40 degrees. Okay, the next one is going to be a 10 ball, and this is 36 degrees, the same as BDNA. Okay, I'm going to show you one more in this series. That'll be the 12 ball. Now what's so special about 12 is that we show 3 sets of quad step. Now to achieve this, I had to make a hierarchy of 12 at 30 degrees. And this is a lot of work. Now when I tried to double the number of balls from 12 to 24, the system slowed right down. Okay, now we're going to change the system to what I call quad step 288. First of all, look at this 360 system I have in front. Now each of these balls are given a 30-degree turn in a full hierarchy of 12. Now when I repeated this process with double the balls, the system slowed right down as if the processor was doing a lot of work. So now I've come up with a faster system which I call Quad Step 288. So let's take a look at it. Now in front I'm showing you a string of 12 balls and an extra helper ring in front. Now watch when I animate this string of 12 balls. Now you can see that the arcs are split into 3 groups. Now let's take it back to the string again and link the 3 groups together in a hierarchy. So now look what we've got. Now we have the first 120-degree configuration using Quad Step 288. Okay, let's double up on this 12 ball to a 24 ball. And now we have 6 quad steps in a string. So we have to link the 6 quad steps into one hierarchy. Now we've produced a nice 24 ball ring. And the speed that things go together is a lot faster than using the Quad Step 360 method. One more thing, if you divide the number of balls, for example 24 into 288, it comes to 12 degrees. Now if we worked with the previous 360 degree system, it would have been 15 degrees. So this system gives us a new circle constant of 288. Something more I'd like to add. 2 12-ball strings can be linked to a 24-ball string as I show. So this method can keep on doubling up. So for people that work in 3 dimension, this is a lot of fun. Now I showed in my earlier videos that these quad step rings can form a lot of different 3D geometry. We'll start with the 4-fold group, and I showed this as a 16-ball ring. Okay, let's double up to a 32-ball ring. I show the 32-ball forming a pine cone in my earlier videos. Now this 32-ball will double up again to a 64-ball. Maybe this doubling up stops at a certain number, because oranges and stuff come in 9 or 10 segments, and flower petals I think are similar. I don't know how many petals you can have on a flower. Okay, the next groups are 3-fold, and they go from 12, 24, 48. Let's start with the 12. Now this low number may be tied up with DNA. This is all uncharted territory. Now this 12 doubles up to a 24 ball. And it's quite plain to see the hexagon arrangements in this 24 ball. Now this 24 ball is going to double up to a 48 ball ring. I showed these as quad step rings in my earlier videos. I showed that the colored balls line up perfectly to the vertices of the Dodeca. Now I've showed the 4-fold and the 3-fold. The only one left is the 5-fold. Now look at the results of this. You can make a pentagon out of each set of colored balls. Isn't that something? Okay, let's double up again to a 40-ball arrangement. If you look at this, you can make 4 decagons with each set of colored balls. Okay, now we'll double up the 40 to an 80-ball setup. Now the thing is, do we really need the 80 balls? And I guess there's no point asking the chaos theory professor, because he keeps on rejecting this 3-dimensional order. Okay, all the rings that I've shown so far are the ones that show the 4 colors. So the number of balls must divide by 4. Because now I want to look at the 60-ball ring. Now as you can see, we can make the 60 ball no problem, because it divides by 4. But I couldn't go half for a 30 because it's not a 32 ball. The ancient Celtic people knew something about this 60 ball ring. Now in front I show how the 30 stones are lining up to the vertices of the Dodeca. Now take a look at the quad step 60 ball ring, and you can see that the 60 balls align both sides of the 30 stones. Now let's take a look at the front view. And now you can see that the structure of Stonehenge aligns up to the 3D geometry of the Dodeca as shown. I sent in a manuscript a couple of years ago showing the duo vectors of the Icosa and Dodeca lined up to the stones of Stonehenge. I received an email from an English examiner and she said, "Thank you for my interest in science, but my manuscript was rejected as unsuitable for publishing." Maybe nobody must contradict the mathematics of chaos theory. Okay, I think we've given enough info on the rings. So now we can give our attention to the slopes. And we're going to start with two very important slopes. Let's take a look at the top one first. Now first you have to know that each colored ball is a spherical cube, 4 angstroms in diameter. Now the angle of this slope and rise is 19.471, which is a Yucatan slope. Now what's amazing of this piece of geometry is that a 24 ball run will produce an 8.5 ball rise, which is 34 angstroms, which is the size of a size 10 Icosa. Okay, now let's take a look at the bottom geometry. And this shows the Icosa slope, which is 26 degrees pico. Now what's amazing about this piece of geometry is that the run and the rise are exactly 2 to 1. And what's amazing is that the slope of the Dodeca gives the height of a size 10 Icosa. And in the bottom one, the slope of the Icosa gives the rise of a size 10 Dodeca. Now what's amazing about this slope geometry is that by using only spherical cubes, we have given ourselves the correct diameter of a spherical Icosa and a spherical Dodeca. Now this has never been achieved by mathematicians that focus on chaos. Okay, now take a look at this. Look how a 72 ball slope can wrap around 3 Icosas. Now I show a Yucatan slope of 72 balls and the horizontal slope is 24 balls. You could call the horizontal slope a 0 degree slope. Okay, now I'm going to show you this animation in the top view. Now you can see that the slope and the horizontal ring, the balls are lining up perfect. Now this only happens if the slope balls are lined up to the run balls in a perfect vertical axis. Okay, now I'm going to show you the slope angle for the Icosa in an animation. And you can see that this produces 3 sine waves in the wavelength of 40 angstroms. This will be the spherical diameter of a size 10 Dodeca. It could also be a size 10 cube. Now I'll show you this anim in the top view. You can see it lining up again. And you can see perfectly that the spiral and the ring are lining up spot on. I've got one more animation to show you. Some people like to study diffraction. This is another example. So I think I've showed enough of this helical order from quad step 288. I think it's a lot better than chaos. So this is Paul saying thank you very much for looking at my video.